See, already we have discussed about that semicircular plate and the circular plate. Okay. Next problem is the bounding is a problem. Write the question. The bounding radii theta equal to 0 and theta equal to pi by 2. Pi by 2 of a circular quadrant. Quadrant are kept at kept at 0 degree C and the temperature along the curve temperature along the curve is kept at 50 into I theta minus 2 theta square degree C. Find the temperature distribution at any point of the plate and also at a by 2 comma pi by 4 if the radius is A. You can draw the diagram for this. So what is given here? Circular quadrant plate. Circular quadrant. Circular quadrant. 90 degrees C. And here theta equal to 0. Theta equal to pi by 2. So what is the temperature of the plate here? Q equal to some f of theta. At theta equal to 0, theta equal to pi by 2, the temperature is 0. So the boundary conditions are one u of r comma theta equal to 0, where 0 less than or less than a. Similarly, second boundary condition is u of r comma pi by 2, r comma pi by 2 equal to 0, r comma pi by 2 equal to 0, where 0 less than or less than a. Okay. Third one is u is finite, u is finite as r tends to 0, u of a comma theta equal to 15 into pi theta minus 2 theta square, where 0 less than theta less than pi by 2. So these are the boundary conditions. Now, what is a two-dimensional heat equation? The two-dimensional heat equation in polar coordinates is dou square u by dou r square plus this one important MCQ already mentioned. This question will come dou u by dou r plus 1 by r square dou square u by dou theta square equal to 0. So what is a suitable solution? May keep it this as equation number 1. The suitable solution is u of r comma theta equal to a r power lambda plus v r power minus lambda c cos lambda theta plus c sin lambda theta. This is equation number 2. Okay. Now applying the boundary condition 1. Applying the boundary condition. So what is the boundary condition 1 here? U of r comma 0 equal to 0. U of r comma 0 equal to 0. Is it not? That is equal to, what is u of r comma 0? Theta equal to 0 na? A r power lambda plus b r power minus lambda into c. So this is not equal to 0. We know that, therefore c equal to 0. So substituting c equal to 0 into substituting c equal to 0 into, we get that u of r comma theta equal to a r power lambda plus b r power minus lambda into d sin lambda theta. This equation number 3. It is the second boundary condition. Applying the boundary condition 2. Applying boundary condition 2. Applying the boundary condition 2 means u of r comma y by 2, that is equal to 0. That means, so u of r comma theta is there, na? Substituting theta equal to pi by 2. A r power lambda plus b r power minus lambda d sine lambda theta equal to pi by 2. Even here you can see that this is not equal to 0. D also not equal to 0. Only sine lambda pi by 2 equal to 0. So what is the next step here? We have to equating to sine n pi. So lambda pi by 2 equal to n pi. Pi by get cancelled. Lambda equal to 2 1. Lambda equal to 2 1. So what is n here? N is any integer. N is an integer. N is an integer here. So lambda equal to 2 1. Substituting lambda equal to 2 1. Substituting lambda equal to 2 1 in equation number 3. Substituting lambda equal to 2 1 in equation number 3, we get that u of r comma theta equal to u of r comma theta equal to a r power lambda, na? A r power 2 1, a r power 2 1 plus b r power minus 2 1 into d sine 2 1 theta. D sine 2 1 theta. So what is the condition here? When r tends to 0, u is finite. U is finite when r tends to 0. So applying this, we will get b equal to 0. So here b equal to 0. Therefore, u of r comma theta will become when b tends to 0. What is u of r comma theta? A r power 2 1 into d sine 2 1 theta. You can take that AD equal to some Bn. Some Bn. Then we can write that therefore u of r comma theta equal to summation of n equal to 1 to infinity. Summation of n equal to 1 to infinity. Bn r power 2 1 sine 2 1 theta. Next we have to find Bn. So to find Bn value, applying the last boundary condition. Applying boundary condition 3. What is boundary condition 3 here? Last boundary condition, u of a comma theta, u of a comma theta, that is equal to some f of theta. So what is f of theta here? 50 into pi theta minus 2 theta square. Actually, this is the condition. Applying that r equal to a here, substituting r equal to a I take this as equation number 4. In 4, we get u of a comma theta equal to summation of n equal to 1 to infinity Vn a power 2n sin 2n theta. So Vn a power 2n, take it as small bn. We are taking Vn a power 2n as small bn, then this u of a comma theta, that means f of theta equal to summation of n equal to 1 to infinity Vn sin 2n theta. So which is half range Fourier sine series, which is the half range Fourier sine series. So in the half range Fourier sine series, what is Bn here? Bn equal to 2 pi L 0 to L f of theta sin n theta d theta. But instead of n theta, what is L here? Length is pi by 2. So 0 less than theta less than pi by 2. In the place of L, you have to substitute pi by 2. That means 2 by pi by 2, 0 to pi by 2. F of theta is what? 50 pi theta minus 2 theta square sine. Okay, it's not n pi x by L. Huh? It's not sine n theta. N pi, please change it. N pi theta by L. That means substitute L equal to pi by 2 here. We'll get that pi by 2 get cancelled. 2 will come here. Sine 2 1 theta d theta. So what is u here? By Bernoulli's formula, it is u. It is dv. Okay. So 4 by pi, and then take it 50 outside. 4 by 4 into 50, 200. 200 by pi. 200 by pi. First keep it u. That means pi theta minus 2 theta square, 2 theta square. Then integration of sine is minus cos 2 1 theta by 2 1 minus differentiation of pi theta minus 2 theta square, pi minus 4 theta. Then integration of cos is minus sine 2 1 theta by 2 1 whole square. 2 1 whole square. Last one is there plus. Differentiation of pi minus 4 theta is minus 4. Integration of minus sine is cos. Cos 2 1 theta divided by 2 1 whole cube. 0 to pi by 2. 0 to pi by 2. So if you are substituting that pi by 2 here, what happened? Pi into pi by 2. You are substituting 0, 0, leave it. You are substituting pi by 2 here, what happened? theta equal to pi by 2, sin n pi it will come. So for this term will be 0 for 0 to pi by 2. So here if you substituting pi by 2 here, what happened? 0 means 0. You will leave it because theta equal to 0, theta equal to 0 here. So the both will be 0. But if you are substituting pi by 2, what happened? Pi by 2 is pi square by 2 minus 2, keep it pi square by 4. So once again you will get pi square by 2. Therefore, the whole thing will be 0 for both upper limit and lower limit. So both terms are 0, only last term is there. Take it that 400 outside minus 4 into 200, 800, 800 by pi, and then in the denominator 2n cube is there. That means 8n cube, 8n cube, cos pi by 2 substitute here, cos n pi, minus cos 0, cos 0. So that is equal to cancel that 100. And then cos n pi we know that minus 1 whole power n minus cos 0 is 1. So this will become as minus 1 whole power n minus 1. But already minus is there. So make it plus, we can change it. So 100 by pi n cube, 100 by pi n cube, hundred by pi n cube, one minus one whole power n. So Bn equal to 0, Bn equal to 0 when n is even. Bn equal to 200 by pi n cube when n is odd. When n is odd. Therefore, what is finally u of r comma theta? U of r comma theta equal to u of r comma theta equal to 200 by pi summation of n equal to 1352 to infinity 1 by n cube r by a whole power 2n sin 2n theta. Okay, this is a solution of the problem. And one more question is there. At the point of u of a by 2 comma pi by 4. What is the point here? You can see that, yeah, at the point of a by 2 comma pi by 4, what is the solution? What is the solution? So u of a by 2 comma pi by 4, that is equal to 200 by pi summation of n equal to odd 1 by n cube r is what? R is a by 2 na, a by 2, a also is there. So a by 2, a get cancel, 1 by 2 or 2 when sin theta is pi by 4. So pi by, if you're substituting pi by 4 here, what happens? Pi by 4. So that pi by 2 get cancelled. So n pi by 2, correct. Sin n pi by 2 is the solution at the point of a by 2 comma pi by 4. Some important MCQ we can discuss. Some important MCQ. Assumptions. Write down. Assumptions on. So this MCQ one dimensional wave equation. One dimensional uh, one dimensional wave equation. Assumptions on transverse vibrations of air. Transverse vibrations. Vibrations of a stretched with elastic string. Assumptions on transverse vibrations of stretched elastic string. Okay, what is meant by stretched elastic string? Already I explained what is called the stretched elastic string. This x-axis, it is y-axis. The string of length L, the string of length L has its two ends and then tightly fixed in two ends. So what are the two ends? X equal to 0. It is revision only. X equal to L. Okay. So here it is like the waveform. So what is the transverse displacement Y? It is transverse displacement function of x comma t, y of x comma t. Okay. First point is the assumptions. Transverse vibration of the string when no external forces act on it. transverse vibration of the string when no external forces act on it. Act on it. Origin is one end of the string. That means this point is 0, comma 0. This point is L, comma 0. We know that. Third point is the motion takes place the motion takes place entirely in one plane. What is the plane here? That plane is called the XY plane. Fourth point is in this plane each particle of string each particle of string moves in a direction moves in a direction perpendicular to the equilibrium position. Perpendicular to the equilibrium position of the string. Equilibrium position of the string. What is called the equilibrium position? So already I told this MCQ actually when I start the class. That means in the first class of one-dimensional wave equation, I explained what is called the equilibrium position. What is called the equilibrium position? Anybody? Equilibrium position is called the rest position of the string. That means string is lying in the x-axis. That position is called the equilibrium position of the string. So what is the next point? Point number
5.
Point number 5. The tension T caused by the tension T caused by stretching the string before fixing it before fixing it at the end. To the end points is constant. Is constant and then important else. The tension T caused by stretching the string before fixing it at the end points is constant at all times. Okay, all times at all points. All points of the deflected string. What is the meaning of deflected? What is the general meaning of deflected? Deflected mean what? The tension T tension T is very large. This is also the important also. The tension T is very large. The tension T is very large compared with the weight. Compared with the weight of the string. Weight of the string and hence the gravitational force may be neglected. So, so from this point number 6 now, not 4, it's point number 7, the effect of friction is negligible. The friction is negligible. What is mean by friction? Friction in the air is very less, so we can approximately negligible the friction when you derive the one-dimensional wave equation. Eighth point is the string is perfectly flexible. Perfectly flexible. It can transmit only tension, but not bending or hearing. As due to the tension is very large when you're fixing on the both the ends. So bending of that string is not possible when it is the full stretch of the string. Bending of the string is not possible, and the shearing forces also not possible. Last one, the slope of the deflection curve. Slope of the deflection curve. The slope of the deflection curve is small, is small, but all points on that all time. So these are the assumptions on transverse vibration of a stretched elastic string. Okay. At least one MCQ will come based on this out of these points. Next one is you know that T, what is M, alpha square is T by M tension by mass, or A square is tension by mass. Okay, what is one dimensional? Okay, next one is assumptions on deriving the one dimensional heat equation. Is for one dimensional heat equation. The last one is for assumptions on one dimensional wave equation. These are the assumptions on one dimensional heat equation. First point, heat flow heat flows from a higher to lower temperature. Second point is the amount of heat required to produce a given temperature change in a body is proportional to the mass. This is in fact proportional to the of the body, mass of the body, and to the temperature change. This constant of proportionality is known as specific is denoted by C of the conducting material. Conducting material. Okay. It is the second point. Third point is the rate at which heat flows. The rate at which heat flows through an area through an area is proportional to the area proportional to the area and to the temperature and to the temperature gradient. Normal to the area. Normal to the area. This constant this constant of proportionality is known as the thermal conductivity. Known as the thermal conductivity. This is one more important MCQ. Thermal conductivity K of the material. Okay. This is the third point. So these are the important assumptions on one-dimensional wave equation and one-dimensional heat equation. So only one more problem is there. This Annulus problem. We will discuss in the next class. So this recording will be saved in M Divya Google Drive.